Okay, good afternoon, everyone. It's time to start our today's Astroph. Today we have three presenters, Thomasan, Shuri, and me. Um, who wants to go first? Shuri, thank you.
Let me share my screen. Okay. So today I will be talking about this paper, which is one of the remarkable discoveries by GWST. That is, they have identified a galaxy at a redshift of 14.44, and they have confirmed it with spectroscopy. So this particular galaxy, they call it Mirage or Miracle Z14. And to give an idea, this redshift of 14, this galaxy is observed just 280 million years after the Big Bang. So at this epoch, that is 280 million years, we expect the universe to be like to be at its infancy with only small, faint, and rare galaxies, like faint galaxies, which are beginning to form. But and there are certain theoretical models, such as these hierarchical uh, structure formation model, which says that it's incredibly rare to find galaxies, and most of these galaxies are small and they are faint. Uh, but with JWST, they have revealed that at photometric redshifts of greater than 10, there are actually a lot of galaxies which are bright for that particular redshift. And so this uh, so to study how these bright galaxies are present, these authors they do a spectroscopic analysis of this one particular galaxy that they have chosen. Next, uh, so for this particular galaxy has an absolute magnitude of -20 in the rest UV spectrum, and they do a 4.4 hour deep observation uh, using JWST prism mode with a resolution of 100, and they see that in their result. Uh, so here they see that this particular galaxy, they have a very sharp Lyman alpha break. That is, they are completely um, not present in bluer wavelength, and they're present in the redder wavelength. And they also show that they have 5 ultraviolet emission line, which has 3 sigma significance each. And after this, they use these emission lines to measure the spectroscopic redshift, and the spectroscopic redshift that they get for this galaxy is around 14.44. And next, they they show that a galaxy, this particular galaxy, which is at the redshift of 14, has the absolute UV magnitude of -20.2, and uh, how other galaxies which are found using JWST, and how do they vary within this spectroscopic redshift. So in the physical properties, they use certain models to get uh, the morphology of the galaxy, and this particular one is extremely compact and resolved, and it has a size of 74 parsec. Uh, which is very tiny, and it's usually compared to star clusters which are present in the local universe. But they also say that it is elongated in the north-south direction, with this being the semi-major axis value. Uh, then they do SED modeling to get the star formation history, and here they show that the this galaxy, it shows a very rapid, or it has a very recent star formation. That is it is around 10 times more star forming than it was in uh, 10 million years ago. So, indicating that the galaxy might be currently undergoing a burst of star formation. And they also do emission line modeling to get the chemical abundances. And from their analysis result, they show that this galaxy has a very significant it's a very significant ionizing source, having um, the eta ionization value of 26.3, and also the ionization parameter being around minus 1.5. Uh, so they uh, they also later confirm using that there is an absence of damping wings, which is not present, which could indicate that this galaxy is the IGM around this galaxy is ionized and has less neutral hydrogen. And the other result that they show is this galaxy has extremely abundant nitrogen to carbon ratio, and which is quite comparable to the sources which is found in the Milky Way globular clusters and the old stars which are formed in the galaxy. So now, conclude this paper. Um, so they say that it is this particular galaxy is a very compact, and it's a very compact galaxy, and it is rapidly star forming, with having an higher chemical abundances for a galaxy at that particular redshift. So yeah, this is the summary of this paper.
Is this the highest redshift?
Yes, yes. As of now, this is the highest redshift galaxy with the spectroscopic confirmation. But I also saw that they also talk about this other galaxy here, which has a very similar redshift, 14.2. Where, yeah, yeah. This other galaxy that they have found using JH is 14.2. So these two are the most distant redshift galaxies just spectroscopically confirmed. Yeah. They say that since they have found abundant chemical ratio and also very extremely high star formation rate at that redshift, they say that using this we could change the lambda CDM model. They do discuss about it, but they say you need this. Yeah, they say you need to get a better or deep spectroscopic observation to comment more on that. But they don't talk more about it. Just they just hint that yes, it does affect it.
How is it affected?
They just say that uh, so at this redshift, the chemical abundance of this galaxy, that is the N by C ratio, is extremely high, and also there is a very strong ionizing component that they find around these galaxies. So, like usually at that redshift, you have the it's the epoch of reionization, or the abundant molecular gas is supposed to be higher than the ionized hydrogen. But they say that the ionized hydrogen is found more than the number density of molecular or atomic hydrogen. So they are saying it's a complicated situation. So you have to which we can't explain using lambda series. Yeah. But they also mention that they get all of this using the SED modeling of the spectra. So, and also their spectra is only 4.4 hours of observation. So they say maybe a better, deeper observation would give a bigger picture on if these ionizing if it has a higher ionized hydrogen, or the number density of neutral hydrogen. Like more better picture on that. That's what I understand. Yeah.
I see the many high open citation lines. Like
Yes.
64.
Yes.
So it is AGN.
No, they say that here uh, they they comment that this is not dominated by a central point source. That is, AGN is not the dominant source of this UV light. It would probably be from the stellar population, not from the AGN. And to explain that, they talk about the C3 emission line, but I haven't read properly about it. Why is it not AGN dominant? But I feel it's a really nice paper. Yes, that is a
Yes, thank you very much. This is very interesting. So I am interested in this abundance pattern. So they are saying similarity between globular cluster
yes,
and this galaxy. And then
yes, here.
does this mean this is actually ancestor of globular clusters, or they are just saying pattern is similar?
I think they are saying that the since they rule out that the UV component is from the AGN, so it could be from high mass stars, and these high mass stars could be forming a globular, like could be in the path of forming a strong globular cluster, because it has a
Okay.
very similar component of what we see in the Milky Way.
I got confused. The size of this galaxy, maybe this galaxy, right, is only 70 parsec.
Yeah, only 74 parts. Yes.
Only 70, right? And the
Yes,
typical
yes.
size of global cluster is say 10 parsec or so, or even smaller. Then I wonder, how do we compare these two things? Say, how about the mass? Do they have mass estimate of this galaxy?
They have mass estimate. I don't remember going through the mass estimate. Maybe I
Maybe it's
missed.
difficult to
Maybe
measure.
I missed.
Oh,
Yeah.
I see.
Yeah, because they only talk more about the size and the emission lines.
Okay.
And since they also somewhere mention the mass is calculated from the UV luminosity, but not more on that. But I don't remember where it
Okay.
was.
I see. Say, basically, this galaxy is not the globular cluster itself, right? Say, globular clusters
No,
may be forming inside this galaxy.
yes, that's
Okay.
what they say.
Okay. Oh, thank you.
Thank you, that's yes.
Oh.
Thank you, Sherry. Is there any other questions or comments to Sherry? If no, we can move on to next presenters.
They do talk about so yeah, Tesla-san, they do mention the mass here. It is around 10 power 8 solar mass, which is similar to the Magellanic Cloud like dwarf galaxy.
Okay, okay. That's a galaxy scale. Okay, 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 okay. I see.
Yeah, yeah.
But it's extremely compact.
Yes, yes.
Oh,
Extremely compact for.
okay. Oh, thank you very much. Oh, so strange.
Okay, thank you. Um, so we can move on to next presenter. I can go next.
Yes, please.
Thank you.
Yes, please.
Um, Today I want to talk about this paper, which they use a Paschen line to predict the mass, black hole mass of the AGN and the luminosity function of the AGNs. They use this formula, which is viral theorem for estimating the mass of the black holes, and they said that RBLR is the size of the broadline region, and delta V2 is the velocity dispersion, which is related to spectroscopy. So by using different emission line spectroscopy, we get different kind of this. And the F factor is related to geometry and kinematics of the BLR. And they use a Paschen line because it's less affected by the dust. And but the problem of Paschen line is that usually become absorbed by the atmospheric region, so it's hard to detect them from um, ground-based telescopes. But with JWST, we can measure the Paschen line features. So they use Cosmos 3D for this mission, and they reduce and extract the spectra by themselves and by some codes in the GitHub. And what they found is that is the one example of their spectra, which they first try to find compact objects to avoid the extended AGN area, and use them based on SNR greater than 5. And then they try to re-extract themselves and visually check that if they have emission line or not, and re-extract by themselves and find the Paschen alpha line for this example. And it's a really detailed paper. I don't want to go to each detail of the method of re-extraction or things that they have done. But the important thing is that they use AGN candidates between redshift 1 to 3, and try to fit the model and find the Paschen line features. And after re-extraction, they find best fit models for their candidates one by one. And the other thing is that yes, and they run MCMC and find the mass relation for a central black hole, and they use FWHM of each line, and the three parameters are given by best fit values for different kind of galaxies, and they try to find luminosity function based on their best fit, and find the one. They use a double power law function, and for some of the candidates they use single power law models, which we can see here. And yes, and they plot the luminosity function for Paschen line path, and we can see that relative to previous luminosity function, they have 3 to 5 times greater in completeness. And so using Paschen line, we can have more completed objects of AGN. And then they try to calculate the Eddington ratio for that 3 models that I've shown, and they use their Paschen line luminosity function to calculate this figure for different Eddington ratio. And we can see that we cannot see a real significant trend for reddened AGN. So they propose that it's because of the fact that maybe their redden feature is because of the line of sight into AGN1, and not because of the central feature of the AGN engine. So they propose that we can put this kind of AGN together and try to act more unified. Yes, and in summary, I should say that they use JWST Cosmos 3D to identify 62 broad Paschen line AGN between redshift 1 to 3. They calibrated new Paschen-based black hole mass and estimate the black hole mass for using Paschen line, and they construct the luminosity function for each of them. And the key result is that this Paschen line selected AGN appear much more completed than optical samples that we have before, and it's likely because near infrared Paschen lines are much less affected by dust. So they said that it's because of this, and they propose that we can act of a redden AGN as the problem of line of sight, not the effect of central engine. Yes, that was the summary of this paper.
Okay, very nice work. So in figure 9, how did they compare Paschen alpha luminosity with optical luminosity? So here, x-axis is Paschen alpha luminosity or Paschen beta luminosity.
Yes.
The previous work is optical or X-ray. So they must have converted this optical or X-ray luminosity to Paschen alpha luminosity to compare.
Yes, I think they did this, but I don't remember the detail of this. But I think they compared these two bit together.
Okay. Yeah, so I was asking, so it's interesting they found the fact of several larger luminosity functions, but then it also depends on this conversion. If conversion is underestimated, then this may be overestimated.
Yes, I think they mentioned that by newer data and newer JWST data, it's maybe different.
Any other questions? Yes, Franca?
Just in continuation with what Thomason said, in figure 6, they have mentioned like a relation of the FWHM of the Passion and MG2. So I think, so they have the spectra from JWST and they search for the optical counterparts from DAISY. And then they fit MG2 from DAISY and Passion from JWST, right? And then they calculate this FWHM relation. So, but since they already have MG2 from DAISY, they can calculate this luminosity factor from that, right? The conversion factor which they require for figure number 9. If you go to figure number 9, as Professor Thomason was saying, that they have used the optical luminosity function from previous work, right? But I'm saying that in their work, they already have the optical and as well as the IR luminosity function. So they can use the factor from this IR to optical and apply it to the previous work.
Yes, yes. They said that they use the NTHU line mass estimator and
Converted to okay. So they do this. And one more question. In figure number 11, you say that for the reddened AGN, we do not see much difference, but trend, yeah. But I think that's expected from the AGN unification model, right? Like we do not, what they conclude that it's basically the line of sight obscuration, but that's what we expect, isn't it? Am I missing something? No. If we would have seen
cannot differentiate this present AGN with other type of AGN, other sort of calculation, and then related to related AGN to the engine of AGN. We said that we can unify each of them together and
yes, indeed, yes, exactly. Okay, so okay, thanks.
Thank you, Priyanka and Thomason, for your comments.
I wonder how does the PN9's luminosity function compare to Angel's or Jimmy's luminosity function? So figure 9 should wait. This is HN. Yeah. So figure 9, it's just factor of 2 or 3 different. It's because of obscuration, right? But then Angel should have obscured luminosity function, right? Should be. So could you compare this with Jimmy? Just follow the conversion in section 3, then you can just compare. You need to convert the x-axis, but then how to do this in section 3? Hopefully, you are not missing too many obscuration. Okay, thank you.
Thank you very much. Any other questions or comments to me?
X-ray is not missing. Perhaps X-ray is also subject to assumption. Okay.
Okay. Thank you. If there are no other questions or comments, we can move on to
Okay. So I need to share the screen. Share. This one? You see it? Yeah. So, okay. So I attended the AGM meeting in Taipei last week. So I want to introduce this summary talk by Soba-san about this Subaru PFS data, which in Taiwan we all can access through Academia Sinica. Okay, so this is something that you can use if you want. Okay, okay, this meeting is focused on AGM. So there are other spectrum, but then this is about AGM. Okay, these are previous things. Okay, here from the AGM. So prime focus spectrograph is something like this. The feature is it's on 8-meter Subaru telescope, and it has very large field of view, 1.5 degree, and it can take 2,400 spectra at one time. So it's it's one of the largest spectrograph on 8-meter telescope. And then they are doing a survey of okay. And another feature of this spectrograph is it can take optical from here to here, and then near-infrared spectra at one shot. This near-infrared part is very unique because usually optical spectra is optical, near-infrared. It's separate instrument, right? But this one has a near-infrared camera as well, so you can take near-infrared J-band, H-band spectra at the same time. So that's very unique. It's different from DAISY. And then collaboration, and then so they are using 360 nights of Subaru 8-meter telescope time to do this 5-year survey. And then cosmology is about 1,000 square degrees. And then this galaxy survey is 12 square degrees, and there are a lot of AGN in both of these surveys. And then we cannot see behind, but anyway, so there's a lot of things to. Okay, so for AGN target selection, there are these, selections. So broadband selection, this is using the color to select broadband AGN, and X-ray AGN, target radio AGN, infrared AGN, subunit AGN, narrowband AGN, and then variability selected AGN. So they are just observing these characters. And then these number of AGN are already observed. And as we can see, here's a 40,000 AGN with 8-meter telescope spectra. So that's something unprecedented and very, very large number. Okay, yeah, and then the survey has just started. These are details maybe you don't need. Yeah, and then also cosmology part. So that was 12 square degrees galaxy evolution survey. And then cosmology survey just do the cosmology, right? BAO and things. There are already 80,000 AGN in cosmology too. So this is a huge sample. So if you want to do some AGN sample, this is the largest sample ever. So you can do a unique science with this. Then let's go. Already summary? How come? Oh no! Okay, in the conference, he showed a lot of spectra, nice spectra here. But then this is a public slide. So he removed this unpublished data. Oh no, this is a bugger. Oh, I cannot show the most important part. But okay, there are a lot of beautiful. He showed in the conference. He showed a lot of beautiful spectra here. Very interesting Goldline AGN. Blah blah blah. Anyway, yeah. Yeah. So these data you can use through academia syndicate. So if you are interested in AGN science, this is a big chance. And then at the Taipei meeting, there are a lot of talks about using a lot of science talks using these spectra. That's the quick summary of the meeting.
Tomo-san, I have a question.
Yes.
Toba-san included this cosmology part, then using, they use quasars for cosmology. Could you talk about a little more about it? What kind of cosmology they want to do?
Cosmology survey is basically doing a baryon acoustic oscillation to measure the dark energy. Yes. So
using
cosmology. No. They use primary targets, whatever is fine for them, because they just want to study the clustering. And then so they target various redshift ranges, galaxy selection. But then when target galaxies, there are a lot of AGNs are included in their galaxy sample.
Yes.
And then that accumulate to 80,000 AGN here.
Maybe I understand. Originally, they have survey for cosmology. Then Toba-san want to understand AGNs from this sample. Am I
yes,
correct?
That's right. Yes.
Okay. I understand.
Yeah. So unfortunately, this Subaru PFS survey was delayed a little bit. Then DEGI's survey, as you know, had started in advance. However, there is some difference. So this is 8-meter telescope, and DEGI is 4-meter telescope. So this can investigate fainter AGN. So that's one thing. And then also near-infrared arm. So DEGI is just optical spectrum, so they don't have near-infrared spectrum. But then this PFS spectra has a near-infrared camera, so we can take near-infrared camera. So that's the two main differences between these two surveys.
Is there any redshift selection?
Sorry.
Is there any redshift selection to these candidates, or just the flux limit?
So which candidates are you talking about? But then for cosmology, they target each redshift ranges because they need to measure BAO from nearby to, I don't know, redshift 1.5 or something like that. So in each beam, they target according to the redshift. For these are selected from, these criteria. So they don't, particularly limit the redshift range. Yeah.
So we have like 80,000 plus 40,000, or do this include some of them?
Okay, this is a little confusing, but 80,000 in the cosmology survey. And the background is galaxy survey. Galaxy survey is I'm a little confused. Galaxy survey number is different. Okay, galaxy survey. This is AGN survey. It's 40,000. And also additional 80,000 is in cosmology survey.
And these are separate, like these are not overlapping.
These are separate regions. Okay. This is generally deeper than the cosmology survey. Cosmology survey is only 30 minutes exposure. These can be longer exposure.
Okay.
They already checked the physical features of AGN, or they extract the spectra, or it's the raw data?
Oh, I mean, those people working on, so the progress depends on, progresses are different in each group, but then some of them are, yeah, extra tests. Oh, wait, I maybe have his email, which show the secret data. Maybe I should show it to you. Right? Give me 1 second? Here, yes. Yes, okay. So this is the same file, but the
share.
oh, I need to share, but including a secret file. No. Not this one. I want to share this. Not this one. But this one. Okay. Okay, let's go and see. Oh, he didn't delete it. Yes! Very nice lecture. So this is one of the real luck AGM upgrade from 1.7, and you can see very nice line feature, hallucinator part, then a lot of lines detected. Nice, right? This one is included ATM, upgrade 0.3. You see narrow band, and oh, there are a lot of Balmer lines here. Very nice. Is BL quasar here. What is this? How about social? Very nice. Look at the SM of the spectra. Nice. What is this? This is the quasar from the Cosmology survey, I think. Yeah, you see a very broad line, amplitude. You can measure particle mass and things like that. This is the 24 quasar. Yeah, very nice. I have a line here. This is already 6 quasars found. But I think this one is already recorded in the previous paper, but not so much. So this is a rediscovery of already recorded ones. But it's still nice to find the relative 6 quasar. This is Simon ratio. Oh, maybe this answers your question. Relative range. So, yeah, those some objects that are relative 6 and 7.
It's interesting that at the peak we do not see much quasars.
What do you mean?
Like at redshift 2 and 3.
Right.
Right.
This one?
Yeah.
Oh,
Maybe this is intentional.
Cosmology survey have relative selection.
Yeah.
They try to get equal enough and evenly. This is comparing spectral Z and photo Z. Oh, this is someone doing black hole mass estimate. So I think Cosmology survey. Cosmology survey, in some redshift they target O2 emitters, and that includes AGN. So you can select AGN among O2 emitters. There are a lot of them. Okay, so these are secret figures. Yeah. Okay. No question? Yeah.
So it's accessible for our group. We can work on.
Sure.
I'm really interested. Thank you. Thank you, Tomo-san. If there is other questions or comments, we can. So if no, we should decide on next week presenters. Any volunteer for oil packing business? Yeah. And
If no one, can you select someone who has less presentation? You have the power.
some students didn't. Maybe Shotaro is here.
Oh,
Thank you.
good,
Thank you.
And then we get one more person.
Mohan, Shotaro, and
Tuesday team usually is John Chin and Chuck.
Mohan, Shotaro, and Tomoki have a list paper presentation.
Okay.
But I should randomly select them and email them.
Yes.
Okay. Thank you. So, thank you for attending. If there's no other specific comments, we can close the meeting now. Thank you all.
Okay. Thank you for her.
Thank you.
And goodbye.
Okay. Have a good weekend.